Hello and welcome to Quantum for High School and College Students, Education and Career Pathways. My name is Don Silberman and I'm the founder of the Optics Institute of Southern California. Before we get started, I want to let you know that all the slides and information in this presentation are available on my website with many links to follow deeper into the topics that I will be presenting. So while you can take notes, you can also just focus on the flow of the presentation. The live version of this presentation may differ because questions may be taken and answered in real time. So some of the details in the scripted notes may be skipped to stay within the allotted time. So who am I and why am I here talking to you? Well, as I mentioned, my name is Don Silberman and I'm the founder of the Optics Institute of Southern California. You can see the logo right under my photograph in this slide. I also maintain an educational website about experiencing life in the quantum age. I'm going to tell you a brief history of my educational career because many years ago, I was your age. I was fortunate to go to a high school that taught astronomy, and then I went to the University of Arizona to study astronomy, physics, engineering, and optics. I've placed the logos of these entities, including the one of the Honors College, which I was nominated to join by one of my professors, not because I had a very high grade point average, but because I was very enthusiastic about physics. He asked me to teach freshman physics laboratory classes when I was a junior and senior in college, and I had a job as a student assistant at the College of Optical Sciences. I also volunteered to be the president of the college chapter of the Society of Physics Students. This allowed me to set up meetings and presentations that I was interested in, and even tours of various scientific and technological facilities around the university. SPS was invited by the Optical Society of America, now Optica, to host a presentation at their annual meeting in Tucson in 1982. I invited my former professor, who was then the acting director of the very first multi-mirror telescope project. I still have a key fob from that very memorable event. After graduating, I became a counselor for the Society of Physics students, and then a member of the Optical Society of America, and eventually SPIE and the Optical Society of Southern California. And there are long stories associated with each of these organizations, including doing education outreach and teaching laser technology to community college and optical engineering at the University of Arizona. And most recently, I've been working on the Ed Quantum project. Before we get into quantum for students, I want to show you this slide and ask if anyone will volunteer to tell me what they see. It's a curious engraving from the Middle Ages of a man seeking to understand the workings of the universe beyond the stars. And we're still doing that today. To understand a little bit about education and career opportunities in the quantum world, I want to guide you in the fine art of critical thinking. I have these questions I like to ask, starting with, what is light? It seems fairly familiar enough, but when you think critically about light, it's a bit elusive. We'll get into that a little bit later in this presentation. The question, what is money, has more to do with career than with science. But again, to think critically about money will be very important in your life. When we talk about trust and truth, all I can say is that each person gets to decide who they trust and what they believe to be true. Quantum mechanics has some very unusual experimental and theoretical truths that I will introduce in this presentation. This presentation will not have much to do with money, trust, truth, or even love. It's just that the words are a bit like light, in that they're not so easy to grasp when you really think about them. When we talk about love, I like to point to my mentors, starting with Frank Memmer. He was my high school astronomy teacher, and then Professors Shea and Bickel were my physics advisors at the University of Arizona. Steve Jacobs was the creator of the optics suitcase, which I learned from, modified, and used to do optics education outreach for many years. Now I am using some quantum optics concepts that grew from the optics suitcase. These mentors and the others pictured here helped me along my career path and showed me kind affection that helped me through many years of life. And then, of course, there's a love I have for my wife and my parents. So the main idea of this slide is to encourage you to help you find your mentors in life, including those of your family and friends and people who will guide you in your career. The main topics of this presentation are divided into 6 sections, starting with what is quantum and why should you care? Followed by quantum computers and cybersecurity, which are 2 main topics that are front and center in the world around us today. There are many more quantum applications that people are studying and working in right now, and there are pathways for students that I'll show you towards the end of this presentation. We have some online and in-person resources to provide, and then I can answer any questions you might have at the end. So what is quantum and why should you care? In this presentation, I will show you that the quantum world underlies our entire modern civilization, and quantum is about to take humanity to the next level. And you can make this happen. Recently, I wrote a short article for a technical business group I belong to titled Quantum Theory with Computer and Cybersecurity Applications. And it starts with this photograph and the following text. The transition from classical to modern physics, including quantum, has dramatically changed our civilization. The people in the above photo ushered in this change beginning over 100 years ago, and the effects are still making exponential change with current and future applications including quantum computer, encryption, sensing, materials development, logistics, communications, and much more. From Wikipedia, we can learn that a quantum is the minimum amount of any physical entity involved in any interaction. This means that the magnitude of the physical property can only take on discrete values consisting of integer multiples of 1 quantum. So for example, a photon of energy is a single quantum of light. You cannot have 1.5 photons or 3/4 of an electron or a fraction of any other quantum entity. Here, a photon of energy is graphically interacting with an atom so that an electron's energy is raised by a discrete amount. On the left is a graphically enhanced photo showing a single photon detector. The reverse can happen as shown on the right with a graphic showing a single photon being emitted from a surface atom of a material. Quantum mechanics does not tell us why this is the case, but the theory, including the energy of a photon, E equals Planck's constant h times the frequency or color of the light of a photon, nu, matches the experimental evidence to such a high degree that our entire modern civilization is based on quantum mechanics, and quantum mechanics has been proven to be true using modern scientific methods. This includes Einstein's famous energy equation, E equals mc squared, where m is the mass of any object and c is the speed of light. Isaac Newton first published his book on optics in 1704 and included information on reflection, refractions, inflections, colors, prisms, and spectroscopy. The discrete Fraunhofer lines shown in this typical solar spectrum are a direct experimental result of the quantum nature of light, and the frequency shown on the x-axis related directly to frequency in Planck's energy equation in the last slide. From Wikipedia, the history of the transistor, We learned that it was not until after World War II when William Shockley decided to attempt to build a triode-like semiconductor device. He secured funding and lab space and went to work on the problem with Bardeen and Brattain. John Bardeen eventually developed a new branch of quantum mechanics known as surface physics to account for the odd behavior they saw, and Bardeen and Walter Brattain eventually succeeded in building a working device. This is the foundation of modern electronics and computers, which our entire modern civilization has been built. With every cell phone, telephone, radio, television, computer, satellite, and all other modern electronic conveniences have their basis in the simple transistor, which is a quantum mechanical device. So why should you care? Because there are educational and career opportunities throughout the sciences that can now use fundamental quantum mechanical principles and devices to help create the next generation of our modern civilization. And for each of you to become knowledgeable and valuable prospective educators and employers, learning about quantum science and technologies at this phase of your educational career will further set you apart from other students vying for those same educational and career opportunities. And you can still get to choose from many fields of study in careers that are shown diagrammatically on this chart from our friends at UC Berkeley Quantum Computing Club. I'll talk more about some of these in a few minutes, but just to list a few of the broad categories, they include quantum chemistry, physics, biology, math, quantum algorithms, quantum simulations, quantum computing, and quantum communications. In December of 2018, the United States federal government passed the National Quantum Initiative that recognized and funded some of the current efforts in developing the quantum industry in the United States. Other countries have done this both before and after the United States, making this a global race to capitalize on the significant progress that has been made in the past decades. On their website at quantum.gov, they have links to the original act and recent reports. I'll talk about the OISC Workforce Development National Strategy Plan in just a few minutes. The Quantum Economic Development Consortium, QED-C, has been established to enable and grow a robust commercial quantum-based industry and associated supply chain in the United States. In the past few years, the amount of attention that has been focused on many advances has left companies, national laboratories, colleges, and universities with many open positions for people skilled with knowledge and experience in quantum technologies. Some very excellent work has been done assessing the needs of the quantum industry. Most of this work has been for people with undergraduate and graduate degrees in physics, chemistry, math, engineering, computer science, material science, and related technologies. In line with some of my past educational endeavors, I've been consulting with Ed Quantum to develop a hybrid curriculum in advanced optics, spectroscopy, and quantum technologies for technicians to fill the workforce gap between those with undergraduate and high school degrees. My colleagues and I at Ed Quantum recently published a paper through SPIE regarding the Ed Quantum program, and this paper, called Quantum Technician Skills and Competencies for the Emerging Quantum 2.0 Industry, is available to be downloaded free from my website. In February of this year, the Executive Office of the President of the United States, the Subcommittee on Quantum Information Science, published the Quantum Information Science Technology Workforce Development National Strategic Plan, which includes the National Q through K Educational Partnership. This strategic plan is also available to download. Here it says, we are educating and training tomorrow's workforce now, and this means you. And on May 4th of this year, the White House announced that the President signed 2 new directives advancing quantum technology. The National Q through 12 Education Partnership has a dedicated website at q12education.org and has many corporate and institutional sponsors. Their aim is to support and grow a quantum workforce that is diverse and equitable, invent new technologies, and drive societal change, and to increase opportunities for students from all backgrounds. My good friend, Dr. Brian Monticelli, wanted me to share with you now in case you might like to take a course in his program beginning in the fall. This is at Pasadena City College, a laser technology program. I was involved with a program like this at Irvine Valley College for about 25 years, and in 2008, Dr. Monticelli took over the program, and 2 years ago we moved it to Pasadena City College, where it's close to the Jet Propulsion Laboratory, and where Brian Monticelli works, and the California Institute of Technology, which has many great science and technology programs, including some with quantum mechanics, and they also have a joint quantum program with Amazon Web Services. The quantum science and technology curriculum will be added to programs like this as soon as we're done developing the course content and the hands-on experiments. The Ed Quantum program is adding quantum education to the laser tech programs that have established over 44 colleges across the country, including Pasadena City College. And here you can see a map of where those 44 partner colleges are across the United States, including Hawaii. So many colleges and universities have dedicated institutes for quantum science and technologies, and this example from Caltech has a nice graphic, and you can find universities and colleges near your home so you can get involved locally. Well, there will be many aspects of modern life that will continue to be affected by the push to integrate quantum technologies into many products and services. I will now focus on quantum computing, encryption, and the internet as they pose the greatest risks and opportunities to people's everyday economic life. Cryptocurrencies have been developed on blockchain technologies and is a fast-growing sector of the modern financial landscape. Blockchain technologies are also being applied to many other industrial sectors, but quantum computer technologies pose a threat to all these currently secure applications. Quantum computers also may be used to hack all other encryption technologies currently in use. A global race is currently being run by private and public entities, some individually and some in consortium, to develop both practical quantum computers and quantum-resistant technologies. Much of the work is being published in the public domain that can be tracked, and some must be held close to the vest, and their progress is unknown to the public. Herein lies the greatest risk. If an unknown entity develops a quantum computer with the capability to hack current encryption technologies and does it without anyone knowing, losses could be substantial. So what's the difference between a classical computer like we have on our desktops today and a quantum computer that may exist in the lab at a university or modern corporate entity? Fundamentally, you might know better classical computer has bits that are independent of each other and can only be in one state at a time, either 0 or 1. In a quantum computer, as we can learn from our friends at the domain of science, a qubit or a quantum bit can be at many states at the same time, and that is a confusing part of quantum mechanics that we need to begin educating many people on how this works. The most important concepts in quantum mechanics that relate to these states are superposition, entanglement, and interference. Quantum entanglement is what Albert Einstein described as spooky action at a distance, and we can discuss that a little bit later in this presentation. A clear example of the differences between a classical computer and a quantum computer is the process of factorization. In a classical computer, we can see that multiplication is easy and quick. 7,177 times 3001 equals 538,177. But to factor 21,538,177 into 7,177 times 3001 is very hard and not efficient in a classical computer. It takes a very long time. However, using the famous Shor's algorithm in a quantum computer, the same factorization problem can be accomplished very quickly. And factorization is used in standard encryption technology all across the internet, all over the globe. So a practical quantum computer with sufficient qubits and error correction can be used to break current encryption technology using Shor's algorithms and other mathematical constructions. There is also the concept that encrypted information could be collected secretly from the current internet and stored until the quantum computer is available to crack the code and read the information later. There are two paths that need to be tracked: the development of quantum computers and their ability to hack secure encrypted information, and the development of quantum-resistant encryption. One parallel technology being developed is quantum secure communications over the internet. Millions and even billions of dollars are being spent on quantum technologies globally, and China is clearly the leader in dollars spent. It is possible that they are also acquiring intellectual property in this domain faster than all other countries combined. So the actual ability to successfully implement effective quantum technologies through trade secrets will likely be the deciding factor winning this global race. The federal government wants to help. In December 2021, the United States Department of Homeland Security published an article titled "DHS Wants State and Local Governments to Start Planning for Quantum Computing, Releases Roadmaps and Resources to Help." This short article describes the situation and mentions that the National Institute of Technology has been working on new quantum-resistant encryption algorithms to provide guidance to US-based entities and will be narrowing down the final entries and releasing the results later this year. This article mentions that the DHS believes quantum computers may be attacking public and private information by 2030. My belief is that it will come much sooner. In this article on Tech Native in December 2021, Alan Grew, the Vice President of Business Development for PQ Shield, a post-quantum crypto solutions company with both hardware and software implementations. He writes about the threat encryption algorithms will face by quantum computers. NIST and partners have been working to define quantum-resistant cryptographic algorithms with the goal of having them fully published standards, and they should be available in 2024. But companies are already implementing post-quantum crypto solutions based on standardized algorithms. Implementation of these algorithms are available, so companies don't have to wait until 2024 to begin migration from classical crypto solutions to the new post-quantum crypto algorithms. My belief that the 2030 DHS time prediction is too long, and that's based on my years of experience in industry and academia with physics, optics, lasers, fiber optics, silicon photonic integrated circuits. And part of that work experience was with a company called PI, Physique Instrumenta, where I helped with applications of fast automated alignment systems for test and measurement of advanced silicon photonic integrated circuits. There are one type of hands-on instruments technicians need to get experience with to help companies bring the next generation photonic quantum computers to the marketplace. In one of the articles in my references, the authors review over a dozen quantum computing hardware technologies and companies that are all in this race to build and implement a practical quantum computer. The details and technical references are all provided for readers interested in exploring them further. My perspective is that quantum photonic integrated circuits will be the winning technology for multiple reasons that are reviewed in a recent blog article that reviews 20 years at light speed, the future of photonic quantum computing. Okay, So that was an introduction to quantum computing and quantum encryption technologies. So we'll leave that behind for the rest of this presentation and talk about many other quantum computing applications in some of the fields of industries seen on this chart from earlier in the presentation. In the next set of slides, I'll review these 9 quantum computing applications in a little more detail so you can see some companies that are already working in areas very important to modern civilization. These include financial services, drug discovery, chemical reaction modeling, the oil and gas industry, data center management, machine learning and analytics, general manufacturing, and telecommunications infrastructure. In addition, you can find more information to each of these case studies in direct links to company websites on my webpage, Quantum for Students. And you can search for more links to information on the industries and fields listed below. IBM is one of the oldest and biggest computer companies in the world, and of course they are at the forefront of quantum computing and applications. One of the most important quantum computing applications is actually in the finance industry. In this composite chart, we can see that IBM has highlighted 4 benefits for using quantum computing: enhancing investment gains, reducing capital requirements, opening new investment opportunities, and improving the identification and management of risk and compliance. Now, one might ask, how does quantum computing benefit those 4 areas of the financial services industry? Using the speed and parallel type processing power of quantum computing on financial problems, particularly those dealing with trading optimization, targeting and predicting financial movements, and profiling many different types of risks, should provide hugely advantageous for those companies that adopt using quantum computers first. Beyond that, greater compliance employing behavioral data to enhance customer engagement and faster reaction to market volatility are some of the specific benefits people expect quantum computing to deliver. Because chemistry is quantum mechanical at its very nature, there are many applications where using a quantum computer will help the process of discovering and engineering new materials in many fields. The ability to more precisely predict and optimize the structure of solid-state materials in semiconductors, magnets, and superconductors will help companies bring advanced new products to markets where their customers will be able to implement them in many different end-user products. High-tech companies making specialty display monitors based on quantum dot and organic LED technologies will move away from the endless trial and error methods to achieve desired brightness and colors by using quantum computer simulation. Pharmaceutical companies using current advanced computing systems to optimize drug discovery will be able to synthesize better drugs faster with quantum computers. And the next generation of optical materials using the molecular structure of proteins and other biomaterials will be enhanced by the use of quantum computers. As you can see by this slide, 4 years ago, the author wrote about using quantum computers in the oil and gas industry. He posed 6 key questions to guide users in the oil and gas organizations toward their holy grail, the driverless supply chain, or how to get oil and gas to customers without tanker trucks. These questions ask about optimizing the process from the reservoir to the end user, optimization limits of siloed supply chain processes, finding the untapped value for separate locally optimized processes, achieving global enterprise objectives aligned with corporate strategies, identifying ideal end-to-end supply chain systems, and creating a roadmap for using quantum computers and figuring out where to start. While this author has written about using quantum computers in the oil and gas industries, these key topics could also be applied to many other industries. In November 2021, Rich Miller wrote an article for Data Center Frontier discussing Google's artificial intelligence lab efforts on creating quantum computing data center. In the article, Rich discusses the differences between classical and quantum computing and the challenges and pathways to create a quantum computer and then scale that up to a quantum data center. These are envisioned to be very different than today's generation of cloud and high-performance data centers due to the significant differences between classical and quantum computing. One main difference pictured here is the cryostat needed for some implementations of a quantum computer. In the article, there is a 3-minute video tour of the Google's artificial intelligence labs where Eric Lucio, a Google research scientist, walks the viewer through their facility and talks through their vision of the future of Google AI quantum computing data center. Rich ends his article by noting that other key players in the quantum computing race are using different technological approaches to build quantum computers, and these may have dramatic effects on the facilities required to make their versions of quantum data centers, especially if the quantum computers can operate at room temperatures, as Celia Merzbacher, the director of the Quantum Economic Development Consortium, described in her keynote talk at the Data Center World in the summer of 2021. This year I had the honor of co-authoring a journal paper with Celia and others associated with the Ed Quantum project that I mentioned a few slides ago, Quantum Technician Skills and Competencies for the Emerging Quantum 2.0 Industry. And that will be published in SPIE's Optical Engineering, but it's already available to download from my website. On the Quantum Mechanical Machine Learning website, you can learn more about the differences between classical and quantum computers and their respective applications using machine learning and data analysis. The advances in fundamental processing methods gained using quantum computing, shown here in the diagram, can lead to extreme advances in pattern recognition, which can be applied to the end user applications such as genetics, self-driving cars, financial investments, logistics, and many more, some of which have already been discussed, and others which I've listed, but we don't have time to discuss them all. This website also has some information about the machine learning efforts from larger key companies like Microsoft, Google, Honeywell, and Amazon. Once again, we look to IBM to help us understand the business use cases in some manufacturing industries to gain a sense of how and why quantum computing seems like such a worthwhile technology to explore and invest time, money, and resources. There is a complete report you can download from this website that highlight, and I quote, the enormous potential that quantum computing is expected to help develop breakthrough products and services that will disrupt and redefine manufacturing. There will be business advantages in these areas shown here on this diagram, with substantial opportunities for early adopters to lock in that followers will have a difficult time overcoming. The last and possibly most important application of quantum computing is when these are networked together in the world's first quantum internet. The University of Arizona is leading the National Science Foundation Center for Quantum Networks with core partners Harvard, MIT, and Yale. The team at the University of Arizona is led by the James C. Wyatt College of Optical Sciences and includes the College of Engineering, the James E. Rogers College of Law, the College of Social Science and Behavioral Sciences. This is due to the significant impact that quantum internet will have on society, workforce development, community outreach, and the legal implications of inclusion. So if any of this sounds interesting for you, and you want to find out how to get involved in the quantum world, I'll give you these 3 main points. Be interested, find a mentor, and take action. To find a good mentor, you might start with your physics teacher or whoever brought this presentation to your school or group. Then, Take action by visiting my website and click on links and read articles that seem to interest you most. There's far too much information for any one person to digest and use it all effectively, so you will need to focus on what interests you the most and find your own path. You can watch YouTube videos. Some are good, others not so much. Maybe you can find some hands-on workshops that you can attend in person or even online. There are colleges and universities that offer courses in quantum science, but not too many that have specific applications like those described in the previous slides. Look for an internship in the field that interests you most, join or start a club at your school, and engage with like-minded fellow students. To help you with the take action step, I've assembled a list of online and in-person resources where you can start your journey. This slide shows a modified screenshot from my webpage, Quantum for Students. This is where you can download a PDF version of the slides and notes and an audio-visual version of this presentation. There are also URL links to all the websites I have referenced already and more that I will view in the time remaining. These include a map of the quantum computing poster, QuizKit, IBM's open source quantum computing resource, Quantapalooza 2020 from Harrisburg University, QViz from St. Andrews University, and Schrodinger's class from the Institute for Quantum Computing at the University of Waterloo in Canada. The Domain of Science YouTube channel and associated posters and books have been made and hosted by Dr. Dominique Walleman, an experimental quantum physicist and author. Out of all the authors and publishers trying to communicate about science topics, and particularly quantum science and computing, I found these to be the most informative, educational, and easy to digest, and even a little bit fun. A couple of slides and concepts that I have used earlier in this presentation have come directly from this map of quantum computing. You can see the graphics in the two red squares, the first one showing the difference between classical and quantum computing, and the second one showing how a quantum computer can factor large numbers much faster than a classical computer. Clearly, I have only scratched the surface of this map and all the topics on quantum computing, but this map and the associated website and YouTube videos are a great place to start. If this has really captured your attention and you want to take the next step to start learning about actually programming on a quantum computer, then IBM has a great open source education system that is free. They call it QuizKit. I'm not going to go into any details about the development tool, but if you're already programming on classical computers, then this could be a great place for you to explore. Harrisburg University of Science and Technology, the Quantum Computing Academy in Harrisburg, Pennsylvania, maintains this Quantapalooza website. They continuously update this endless list of free online learning opportunities for the quantum computing community. They have 10 upcoming events listed on this webpage, like the one that just happened on May 4th, Quantum Computing and Machine Learning. The Quantum Mechanics Visualization Project, developed and maintained by the University of St. Andrews School of Physics and Astronomy in the United Kingdom, offers students the ability to use very good graphical simulations to learn more about the fundamentals of quantum mechanics, which can help them understand some of the non-intuitive outcomes of various physical experiments and the mathematics that describe them. There are many different introductory and advanced topics to choose from, including a few applications such as quantum cryptography that I mentioned earlier. In this quantum key distribution simulation and challenge, the student has provided a detailed description of the physics experiment, in this case using familiar polarization filters and a single photon source as the quantum object. The student's goal is to help Alice and Bob determine if they have a secure quantum key that has been distributed without Eve eavesdropping. The student can watch a simulation of the experiment using several polarization settings to display and maintain controls. Here I have used the continuous setting with all the display controls shown. In this slide, I show my results of the challenge where I chose the correct sequence of detections, assuming there was no eavesdropping. There are many more variations in this simulation and challenge the students can go through to further their understanding of this experiment. This can lead to a deeper understanding of quantum science in general and quantum cryptography in particular. Last summer, I attended a 2-day online workshop where I learned how to provide short course on quantum science to high school students. This was offered by the University of Waterloo in Canada and was called Schrodinger's Class, after the famous quantum scientist Erwin Schrödinger and his conceptual cat. I have the complete set of all the course materials for students and teachers who can work with your teachers to help bring this unique educational opportunity to your school. Some of the concepts are similar to the simulation and challenge I just described from the University of St. Andrews. We are now at the end of this presentation. If you think this is something you want to learn more about, then follow the white rabbit into the new quantum world of superposition, entanglement, and interference, or as Albert Einstein named it, spooky at a distance. It's always been a goal of mine to better understand the quantum world, and now I have finally jumped down the rabbit hole and am hoping to guide many students. If you have any questions you'd like to ask, you can contact me directly from my website. Just follow the digital white rabbit. We are living in the quantum world where the smallest subatomic particles and energy fields make up everything in our macro world. These new quantum technologies built on quantum science is taking humanity to the next level of our modern civilization and likely to many worlds beyond. And you can be a part of making all this happen. If you have time, there is a 3-minute video we can watch from the Q through 12 education website.